Number 1 on the multiple choice. A study of voting chose 663 registered voters at random shortly after an election. Of these, 72% said they had voted in the election. Election records show that only 56% of voters registered voted in the election. Which of the following statements is true about the boldface terms? For this problem, the correct answer was letter C, in that the 72% is the statistic, where 56% is the parameter. Remember, the statistic comes from the sample, so the 72% came from the sample of 663 voters, whereas the 56% represents all of the voters that are registered out there, which is considered our population. Also, parameter is for population, so just remember kind of the P and the P on that can help you make that connection. In addition, parameters tend to be in terms of the variables they use are Greek alphabet letters such as mu and sigma, whereas statistics tend to be our kind of normal alphabet like the letter P or the letter S. Question 2. The Gallup poll has decided to increase the size of its random sample of voters from about 1,500 people to about 4,000 people right before an election. The poll is designed to estimate the proportion of voters who favor a new law, banning smoking in public buildings. The effect to this increase is to do what? Overall, what they are doing then is increasing their sample size from 1,500 to 4,000. When you increase sample size, the reason you're going to do that is letter C, to reduce the variability of an estimate. It's very important that you make the connection that a larger sample size gives you lower variability. By the way, variability is another word for your standard deviation or your spread. This concept will be used for the remainder of our book. Question 3. Suppose we select an SRS of size 100 from a large population having proportion P of successes. This is sigma P hat is the symbol for this, by the way. So it's sigma P hat. Be the proportion of successes in a sample. For which value of P would it be safe to use the normal approximation to the sampling distribution of sigma P hat, this notation here? Now, from this problem, we know that we are dealing with proportions. In proportions, we know that we have to test that the sample size is greater than or equal to 10. The formula for that is to show that n times P is greater than or equal to 10, and then we also show its complement that n times 1 minus P also has to be greater than or equal to 10. If both of these conditions are met, then we can go ahead and compute a new standard deviation. So if we go ahead, and what we know about the formula is that n is 100. So we have to have 100 and then some probability value such that this will be greater than 10, whatever the P is, and then 100, and then the complement of that also is going to have to be greater than or equal to 10. If you go through this and try it, what value is going to work for your probability? If we were to try letter A, what's going to happen on that one, this first formula would actually fail because this condition would not be met. For letter B, if we try 1/11th, again, this condition would not be met. For letter C, if you try 0.85 for probability, this condition would be met. You're going to have 85 is greater than or equal to 10. Well, if it works in this one, try here. 1 minus 0.85 would be 0.15 times 100 would be 15. This condition would be met. So we actually did just find the correct answer here. Again, is the answer letter C. If you continue on, you're going to notice that D and E both meet this first condition, but will fail when you try the second condition. Question 4. The central limit theorem is important in statistics because it allows us to use the normal distribution to make inferences concerning the population mean. In what condition is that true? The correct answer for this one is actually going to be answer A, which states that the sample size is reasonably large for any population. The key to remember about the central limit theorem is we use that when we do not know the shape of the population. So that's why letter B is not correct. If the population is normally distributed, Well, if it's normally distributed, we don't even need to use the central limit theorem. If they tell us the population is normally distributed, I know the sample will be. Same with letter C, that's irrelevant, and also letter D is irrelevant. Now letter E, if the population size is reasonably large, whether the population distribution is known or not. The central limit theorem does not look at the population size. The central limit theorem looks at the sample size to make a decision. Remember, for this case, we're doing this for continuous data, and if the sample size is greater than or equal to 30, means the central limit theorem is met, and we can assume that any distribution is approximately normal. Question 5. The number of undergraduates at Johns Hopkins University is approximately 2,000, while the number of Ohio State University is approximately 40,000. At both schools, a simple random sample of about 3% of the undergraduates is taken. Each sample is used to estimate the proportion P of all the students at the university who own an iPod. Suppose that the fact that P equals 0.8, this is a population parameter here, at both schools. Which of the following is the best conclusion? Now, one thing we can tell, Johns Hopkins has by far a smaller sample size, and Ohio State has a much larger sample size. The sample size alone is going to tell you that the variability at Ohio State is going to be less variable in the data, where Johns Hopkins will have more variability. So if we look at that letter A, the estimate from Johns Hopkins has less sampling variability. That's absolutely false on that one, so cross it off. For letter B, the estimate that Johns Hopkins has more variability than that from Ohio State is going to be the correct answer here. Now letter C says here the two estimates have about the same sampling variability. These sample sizes are nowhere near the same. Letter D, it's impossible to make any statements about variability. We absolutely can if we have an understanding of the sample size. And then clearly letter E is not adequate because we know answer B does make reasonable sense. Question 6. A researcher initially plans to take an SRS of size n from a population that has a mean 80 and standard deviation of 20. If he were to double his sample size, that is to use 2n, the standard deviation of the sampling distribution of the sample mean would be multiplied by what value? Now, since we're talking about standard deviation, there are two different types. There's a standard deviation of the proportions and the standard deviation of the means. They don't specify the type of data, so I'm going to look at both. The standard deviation of p hat by definition is the square root of p, and then times 1 minus p all over n. And then the standard deviation of the means would be the sigma of x bar is equal to sigma divided by the square root of n. Where in this case, keep in mind sigma here is the population standard deviation, p here is the population proportion. Both of these elements are parameters. So looking at either one, what's going to happen, n is going to change to 2n. So if we do that and we multiply 2 into either one, what's going to happen to the standard deviation? The difference is you're going to see, I'm going to actually go to the means one because it's easier to look at. What I could do to look at it more visually is I could break this up, bring out the square root of 2, and keep this as a square root of n. When I do that, what I notice is that here is the initial standard deviation formula. When you multiplied it, the population, or the sample, I'm sorry, by 2, what happened is we're going to see it's the standard deviation is now multiplied by 1 over the square root of 2. Therefore, letter B is going to be the correct answer. You could do the same analysis if you want to look at the proportions one. If we kind of factor this out, that 2, you're just going to see here that the 2 would kind of come out, and then over here you could still have your original formula that we're used to seeing, and then you're going to see that it is going to be underneath the square root. And then what we would do is you could factor out this, which is the square root of 1 over the square root of 2, which is the same answer. So looking at either standard deviation formula would give you the same result. Question 7. A student newspaper at a large university asks an SRS of 250 undergraduates, do you favor eliminating the carnival from the term end celebration? In all, 150 of the 250 are in favor. Suppose that the unknown to you 55% of all undergraduates favor eliminating the carnival. If you took a very large number of SRSs of size 250 from this population, the sampling distribution from the sample proportion, this is again going to be, kind of shows weird on their printout, sigma of p hat would be what? So they are talking about sigma of p hat, and they're telling us it's a proportions, but we could have gotten that from here. These results are not means, it's a proportion result that they got. So what I would do for this one is to reflect back on the formula for finding this, and remember the formula for sigma of p hat is going to be the square root of p times 1 minus p over your sample size of n. Because they want to know about the complete sampling distribution, we also have to factor in what is the mean. So the mean of p hat is equal to the p-value. Again, this is the population parameter for that. Now be careful, the population parameter, they told us the true population answer is 55%. So what we can do is we can change this to be 55% or 0.55. Based on that alone, we are looking at either these three options. We know C and D are not valid. Now if you look at the standard deviations, they all do have the same standard deviations, but let's just confirm it. The calculation you would do for this is going to be the parameter value, so the true population is 0.55. 1 minus 0.55 would be 0.45, and then over our sample size of 250. If you do compute this, you're going to get those same three answers. So then it comes down to the type of sampling distribution in terms of shape. Is it heavily skewed? Is it approximately normal? Or is it exactly normal? To say if it's exactly normal, what you would have to have them say is that the population distribution is normal. Nowhere in here do they ever say the population is normal. Because of that, it cannot be considered exactly normal. Now, is it approximately normal or skewed? To see if it's approximately normal, you want to see if it meets the requirements. Remember the requirements to say approximately normal is going to be for proportions, n times p and n times 1 minus p. Both of these have to end up being greater than or equal to 10. So if you put in here 250 times our 0.55, that clearly is greater than 10. And if we do 250 times the 0.45, that is greater than or equal to 10. Because of that, this condition allows us to say that it is going to be approximately normal, and letter B is the correct answer in terms of giving us the appropriate shape, the center, and the spread measurement. A good reminder is, remember from chapter 1 when they said describe the distribution, we always said don't forget your socks. And that's why they always address, again, the three components of shape, center, and spread when we reevaluate any distribution. Number 8, which of the following statements about the sampling distribution of the sample mean is incorrect? Now remember the sampling distribution for sample means would be our formula of mu of x bar, and we know that equals mu, and sigma of x bar, which equals sigma over the square root of n. Again, where n is our sample size, sigma here is the population standard deviation, mu is the population mean. And we're looking for which one is incorrect. So if we go through and we start with part A, the standard deviation of the sampling distribution will decrease as the sample size increases. Well, if you just think about it from here, make up some numbers. Maybe the standard deviation was 0.5. If we did 0.5 over a sample size of 10 versus they're saying here, what happens if the sample size increases? So try 10 and try 100. What's going to happen? Will the standard deviation decrease as sample size increases? Absolutely. Either think about it numerically or think about it from this perspective. As you increase sample size, you reduce variability. That's what happens. Variability is standard deviation, so it is not letter A. That is a correct statement. Letter B, the standard deviation of the sampling distribution is a measure of variability. True. Of the sample mean among repeated samples. That definitely is just the definition of it. Standard deviation measures variability, and the standard deviation of the means means they did many, many samples of a certain sample size. So by definition, letter B is a correct statement. Letter C, the sample mean is an unbiased estimator of the true population mean. Now, the point of this one, that we can make this connection about the mean of x bar is equal to mu, we're making that connection that the parameter of the population is being used for the sample is because it's unbiased. If it was considered a biased estimator, what we would know is the mean of all the sample means would be completely different from the population mean. So when the mean of all the sample means is very different from the true population mean, that's a biased estimator. So it is unbiased by definition. Letter D, the sampling distribution shows how the sample mean will vary in repeated samples. Again, a sampling distribution, right here when we do, again, mu of x bar and sigma of x bar, means we took many, many samples. So in repeated samples, this mean does reflect what would happen in repeated samples. By default, the only other answer technically would have to be E. That would have to be the incorrect one. It says here, the sampling distribution shows how the sample was distributed among the sample mean. This is absolutely incorrect because they say among or around the sample mean. It's not about one sample, it's about many, many samples of the same sample size. Number 9, a machine is designed to fill 16-ounce bottles of shampoo when the machine is working properly. The mean amount poured into the bottles is 16.05 ounces and the standard deviation of 0.1 ounce. Assume that the machine is working properly. If 4 bottles are randomly selected each hour and the number of ounces in each bottle is measured, then 95% of the observations should occur in which interval? So what we're dealing with here is they want to know which interval, and we need to first think about what is the shape, the center, and the spread of this data. Nowhere in this problem do they tell us that the machine data is normally distributed. So what we have to do is check some conditions. Looking at this, are we talking about the means or the proportions? In this case, we are looking at the means. So we would need to look at and find out what is the mu of x bar, evaluate kind of a sigma of x bar, so we'd have center and spread, and then we'd have to look at the shape. Now, we're trying to assume, if we can, and we'll get to this in a second, if it's approximately normal. If it is approximately normal, that would allow us to compute a new mean of mu of x bar. We would be able to have our new standard deviation, and we could compute that. And then what we could do is they're looking for where 95% of the observations would occur. Well, think about it from this in Chapter 2. 95% of the observations, we're looking for 95% of the curve is right there to the right and to the left of mu. So if we can find that, the area under the curve, they would want us to compute what this value would be and what this value would be. That's the interval they're talking about. Now, if we can do the means, by the way, we do know that the mu of x bar is just equal to mu. Well, we know what mu is. So mu of x bar, what I know, would have to be 16.05. So that is what this mean value is at 16.05. They want to know, if we go to the right and to the left here, how far can we go such that the area under the curve is 95%. Now, from Chapter 2, what we talked about for this would be using inverse norm. So remember, if we did it, we would come in here and say inverse norm. And the area we would want is from here to there. Now, that area under the curve, 95% is the green. This extra little tail would have to be another 2.5%. So we would be looking for 0.975% under the curve. And then I would type in the new mean and the new standard deviation, and I would compute. And what it would give me is this value right here. Okay? We could then also compute this value here. Now, if we know the mean was 16.05, so I would type that in. What would the new standard deviation be? Well, remember the formula for standard deviation is going to be sigma over the square root of n. So what we could do for this is we know that sigma is 0.1. The sample size here is 4 bottles, so it would be over the square root of n, or the number 2, basically. That'd be our standard deviation. So I could type in, 0.1 over 2 as standard deviation, and I could compute this out. Now, when you do that, you're going to end up getting, for this side here, it's going to look like it's 16.15. Now, could we find the value that's to the left? Sure, we can just modify this formula. Instead of finding the area at 0.975, we would change this to 0.025, and we could find the third value. And it would look like the lower end is this boundary. Now, I got to tell you, this is not the right answer. The correct answer for this one is technically going to be E, because even though the calculations work, are the conditions met? So to meet the conditions, remember we have to check for randomness, independence, and normalcy. Now, are these randomly selected? Yes, the random condition is met, so that's fine. Has independence been met? The test for independence, when we are doing the means, is you have to show that our population, which is capital N, is greater than or equal to the sample size times 10, or 10 times the sample size. Fine. The population, I don't know what it is, but our sample is 4. So 4 times 10, is it logical to say that the population is greater than or equal to 40? Yes, it makes sense that the population is greater than or equal to 40. Now, because we were able to show that independence would be appropriate, the independence condition is met, that actually allowed us to compute the standard deviation and change it. If this independence condition was not met and it was false, we could not adjust the standard deviation. It's illegal to do in this. But we're fine. So random and independence has been met. Now the last condition that we would have to check is normalcy. The normalcy condition, if we check for that one, is actually going to allow us to use inverse norm and assume that the shape is approximately normal. Now the condition for normalcy, if you want to check if it's a normal or approximately normal distribution for the means, is the central limit theorem. And that would be either they're telling us in this problem that the population is normal, which they haven't. Because they haven't told us the population is normal, we must use the central limit theorem. So the test for this is the sample size greater than or equal to 30? Well, in this case, our sample size that we're using is 4. 4 is not greater than or equal to 30, so the check for being approximately normal is not met. Because it's not met, we are not allowed to assume the shape is approximately normal, which therefore we cannot do inverse norm, which makes none of these answers valid, even if you use the appropriate methods, and none of the above is the correct answer because not all the conditions are met. Number 10. Suppose that you are a student aide in a library and agree to be paid according to the random pay system. Each week the librarian flips a coin. If the coin comes up heads, your pay for the week is $80. If it comes up tails, your pay for the week is $40. You work for the library for 100 weeks. Suppose we chose an SRS of 2 weeks and calculate your average earnings at X. The shape of the sampling distribution will be what? Now in this case we want to think about, is this going to be a means or proportions? The value for pay is a continuous variable and it's not proportion, so we are talking about the means. So I'm just going to kind of jot down mu of x bar, sigma of x bar is our concept. They do want to know about the shape. Is it approximately normal? Now to show approximately normal, if we're talking the means, what we want to consider is the central limit theorem, where n is greater than or equal to 30, or they're going to tell us in the problem. Now, nowhere in this problem do they mention anything about being a normal already, so we can't assume that. So we would have to do some type of test on here. Now, the other facts we know about this is that our sample size in SRS is of 2 weeks, so n is equal to 2. Now, if we do this, our complete time of the population is 100 weeks. That's interesting to know, but not necessarily needed right now. If we do that, n of 2 is going to tell us that's not a true statement. So approximately normal is not met. So what we do know, we know it's not normal because they don't say it in the initial problem. We can't say approximately normal because the condition is not met. Now, which one of the other 3 is it? In order to figure out if it's C, D, or E, you want to actually make a sketch of what this distribution would look like. So for 2-week sample size, if you think about it, the possible outcomes of week 1 and week 2. So if I have week 1 and week 2, I could get heads or tails, I could get heads or tails. There's 4 possible outcomes. The outcomes that could be flipped would be tails and tails, tails and heads and tails, and then heads and heads. So if you were to sketch this just in a real kind of crude format on maybe making a dot plot, what about the combination of tails, 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 heads, and heads, tails is going to be the same output for that one, and then heads, heads. If you get tails, tails, by the way, we can tell that the pay for that one is going to be $80 total, 40 and 40. That's why I have it on the lower end of the graph. Tails, heads would be 80 and 40, so this would be a 120. This other one would be a 120. And two heads would be 160. That's why I put the two heads on the far end. So if you want the dollar amounts associated with that, you could do that, which probably would make a good sense, all right? So $80, 120, and then our 160. Now, if you were to go ahead and put the dot plot together for this, what we're going to find is we have one result here, two results here, one result here. Now, the question is about the shape. So we cannot say it's approximately normal. Careful, this problem too, they're saying normal. When they say here just normal in general, that would be that the population was stated as normal. When we check the condition, that's for approximately normal, so be careful with your wording. We clearly know it's not normal, nor is it approximately normal. However, when you look at this, we can tell the shape of the distribution is clearly going to be symmetric. The first free response, number 11. Below are histograms of the values taken by 3 sample statistics in several hundred samples from the same population. The true value of the population parameter is marked with an arrow on each histogram. Which statistic would provide the best estimate of the parameter? Explain why. So what we know are these arrows measure the true p hat, or the true p value. So this here is going to be the true population parameter is what we're looking at. Now, this is a sampling distribution, so we are looking at the mu's of p hats because we're talking population parameters of proportions. So this is the mean of the p hats. They have sketched all of the means of the various samples and came up with these histograms. What we're looking for, to find the one that is the best estimators, we want the most unbiased. The most unbiased is going to have the true population parameter, which is P, is going to be in the middle of your distribution. This looks like it's very much in the center. This looks like it's very much in the center. And this one here is definitely not as much in the center as we would expect. The center of this data, because it is skewed to the right, so remember, skewed to the right means the mean is going to be pulled more to the right, but the median is going to be more over here, so it's not really in the center. So letter C is not a good one at that. The next to choose between A and B, those A and B are unbiased, but what we're looking for is the one with the least amount of spread or the lowest variability. So we want to have low bias and we want to have low variability. So based on that, letter A has both the low bias, which we do see in both A and B, but it has less variability than graph B because more of the data is at the center in this distribution. Question 12. The amount that households pay service providers for access to the internet varies quite a bit, but the mean monthly fee is $28 and the standard deviation is 10. The distribution is not normal. Many households pay about $10 for limited dial-up access or about $30 for unlimited dialed-up access, but some pay much more for faster connections. A sample survey asks an SRS of 500 households with internet access how much they pay. Let X be the mean amount paid. Part A. Explain why you can't determine the probability that the amount of randomly selected household pays for access to the internet exceeds $29. So what they're saying is, why can we not come in here and say, find the probability that X is greater than 29? The key to this problem is that we are talking about a randomly selected household. So this is one household. What they've done here is they took an SRS of 500 households. The data that we have only deals with our simple random sample, not one households. So we do not know the shape of the distribution of an individual household pays for internet service. Because of that, we don't know, we can't state the mean or the standard deviation for that in order for us to evaluate the shape of it. Letter B. What are the mean and standard deviation of the sampling distribution? So again, we're talking about the SRSs of 500. So based on this, we are talking about the means, not the proportions. So we want to compute the mu of x bar, and we want to compute the sigma of x bar. Now, in order to do the mean, we can just go ahead. We know mu of x bar is just equal to the mu of the population. They've told us the population mean is 28, so we're going to say that's $28. Now, in order for us to compute the sigma of x bar, we must first check for independence or the 10% condition. So on this side, I'm just going to put the 10% condition, and we know for that one we must show that the population of n is greater than or equal to 10 times the sample size. Our sample size is 500, so we must have at least a population of 5,000 different households in here. They haven't told us specifically how many households there are, but we can assume that there are at least 5,000 households with internet service. That does make sense. So we're assuming this condition makes sense. Based on that, we are now allowed to come on in and compute the new standard deviation. Remember, that's just sigma over the square root of n. Based on that, that's going to be 10, which is the standard deviation of the population, over the square root of 500. And then our new standard deviation here is going to be 0.4472. Now we've done center and we've done spread. Part C asks us about the shape. Because we are looking at the shape and it's for the means, what we're going to do here is use the central limit theorem. The central limit theorem wants to show if n is greater than or equal to 30. All I need to do here is we have 500 is greater than or equal to 30. Because that is met, we definitely can say that it is approximately normal. Again, keep in mind the first thing I do want to check is, does the problem itself even say it's normal? It doesn't. It says it's not normal, so we cannot assume exact normalcy from here. We can only do approximately normal. Now they're going to roll back around and ask us that same question in part A, but in part D it's different. Find the probability that the average fee paid by the sample of households, not a single one, exceeds $29. So what they're asking here, it is a little bit different than in question 1. In question 1, they want to know the probability that x was greater than 29. Here I want to know the probability that x bar is greater than 29. I want the average fee. Can we do that? Absolutely. What we want to know, if it's greater than 29, feel free if you want to sketch the distribution, you could. We know that the new mean is 28. The standard deviation is 0.4472. I want to know if it's greater than 29. So what we're looking at on the curve is from 29 on up. This is basically just chapter 2 coming back. This is a normal CDF calculation because we have approved or shown that it's approximately normal. I went from 29 up to negative 999. And I just used the new mean and standard deviation that I computed from above. And I would just type in 28. And I would do 0.4472, close that out. Ignore that parentheses there. And if you compute this, what you're going to end up getting is that the probability is 0.0125. Now, let me caution you on one thing. Let's say this was its only question on the free response was this letter D. If we did this for calculator speak, a couple things you'd have to do. You must say it's approximately normal somewhere on here, but we already have. We did that above. Now for the calculator speak, I'm going to cover myself here, and I'm going to put that this is mu of x bar, and that this is sigma of x bar. So based on that, we know that we have stated our parameters that are necessary for calculator speak, and the AP board would give us full credit for this problem. Question 13. According to the government data, 22% of American children under the age of 6 live in households with incomes less than the official poverty level. A study of learning in early childhood chooses an SRS of 300 children. Find the probability that more than 20% of the sample are from poverty households. Be sure to check that you can use the normal approximation. So the first thing you want to do when you have a problem like this is look at the problem and figure out if it's proportions or a means problem. When you take a look at this with the percentages, we can tell that it's proportions. So we ultimately are hoping that we can do a normal CDF calculation using the mean and standard deviation of the proportions. So we need to find those. So the first goal is to figure out the mu of p hat and sigma of p hat. Because if we have the mean and standard deviation, then as long as we know the boundary levels we're looking for, then we could go ahead and compute that answer. So from this, what we want to figure out is that the mu of p hat is going to be, the p is the population parameter. We can tell from here that the population percent is 22%, so I'm going to put 0.22. Now, sigma of p hat, we know by definition from our formula, is the square root of p times 1 minus p over n, where n is our sample size, and p is the population parameter for the proportion. Now, we are not allowed to actually compute a new standard deviation unless we show that there's independence. So we want to make sure that we address the independence for our new spread calculation. The test for independence is going to be our 10% condition. So we want to check, is the population greater than or equal to 10 times the sample size? In here, we can tell our sample size is 300. So is the population greater than or equal to 3,000? Now, they haven't addressed the actual population size here, but it's reasonable to assume the population of people in poverty is going to be greater than 3,000 individuals. Because of that, we can go ahead and now we can compute our new standard deviation calculation. Putting in our population parameter is 22%. 1 minus that is 0.78. And again, our sample size is 300. That's going to give us a standard deviation of 0.0239. So we have tested for independence, and I'm actually going to put that right here, that this was for independence. We do want to check, though, for normalcy or for randomness also. We do know here that they took an SRS, which is a random sample. So I'm going to put that it is random. So we have random and independence. Now let's check for normalcy. Because we're dealing with proportions, we know if we want to show that something is approximately normal, what we need to do for that is we need to show that n times p is greater than 10, and that the complement of that, n times 1 minus p, is also greater than or equal to 10. Based on our statistics that we have, again, our sample size here is 300, p is 0.22. This is going to be 66, which is greater than or equal to 10. That condition's met. The next condition would be the 300, and we're going to have the 0.78. That's going to give us 234, which is greater than or equal to 10. So again, that's met. So we can say it's approximately normal. So now we have our center, our shape, and our spread for this new distribution. All we have to do now is wrap up and actually answer the probability question. So looking back, the question is to say right here, find the probability that more than 20% of the sample are from the poverty households. So to do that, we're going to say, let's find the probability that p hat of our actual sample is greater than or equal to 20%. If we were to make a sketch of this distribution, by the way, looking at it, just to get a general idea, the mean of the distribution for the population is 0.22. What's the probability that our sample is at 20%, which 20% is probably about right there, or higher? So back from Chapter 2, we can definitely do a normal CDF calculation for that. As we can tell by the picture, our lower bound is going to be 0.2. The upper bound in this case is going to be a 999, just a large number. And then our mean for here, 0.22. Our standard deviation is going to be the 0.0239. Again, if we were doing calculator speak, or since we are doing the calculator speak, we need to make sure that we've defined our calculator speak. We have said it's approximately normal, which you can't assume normal CDF means normal for that one. And for our parameters, what I'm going to do is I'm just going to put here that this is mu of p hat, and this is sigma of p hat to cover ourselves for calculator speak. And then the final answer on this one, the probability when you put that in your calculator, comes out to be 0.7986. So then we could then state this answer in context of the problem. We could say here there is an 80% chance that in a sample of 300 children, more than 20% are from poverty households.